be.
Yeah. Am I audible now?
Yes. Much audible,
Yeah.
much better
So,
now.
Sir,
yeah.
your
So,
voice is breaking. I don't know. I think connection issue.
It should it should not break now. I have switched my place, so sorry about it.
Okay.
okay, so there were a couple of like prep courses that zero learning courses that we had to go through. So I could complete only a few. So will it have a lot of impact for this first session because we could complete it maybe a little today like that. So just wanted to check for today's session. Is it going to be difficult then?
No. See, if you have done that course, it's good. If you have not, it's not going to affect you. Okay, so don't worry about it.
Okay. Okay. Thank you.
Okay, so don't worry about it at all. You would be able to get a gist of what we are going to learn. And eventually, I have told you that we will be going slow. Don't worry about picking up pace with what is being told. It's just that in the initial few sessions, it might be very uncomfortable with the way I approach the subject because I see there is a gap in terms of how we have been told maths and how we have been uh, visualized maths. I would rather say that. So a lot of things which has happened to you in your schools or in your engineering or whatever courses that you did, they have taught you in a perspective. I'm not saying that that's wrong. I'm just saying that it is a very different construct altogether. But the kind of application oriented knowledge that you need, at least from machine learning point of view, it's slightly different. And this is what I got to know. I did my master's at Indian Statistical Institute. I don't know whether some of you know about it or not. So ISI is one of the not best, but it is one of the good institutes in India. And when I went there, I realized how maths should be seen as maths. Okay, so I would try to impart that knowledge to you. I would try to help you understand all of those things from that perspective, at least if not in ML, but how everything links together, the maths part that you're studying here, how that gets linked to the machine learning part, or how the statistics part get links to the machine learning part. It is all connected. So you should be able to feel or enjoy everything maybe in 2 3 lectures, and then it would be more convenient for you. Okay, good.
Hi, sir. Good morning. We will be having these classes only on weekends, right? Because as we are working professionals, weekdays classes will be a bit tough for us to attend. So can you just please confirm on that?
Yes, it would be all on the weekends. The schedule is already there. Whatever you
Okay.
have right now, and that is how it should be in the coming
Uh,
days.
All right. Thank you.
Okay. Any other questions before we begin? And I'm when I say begin, I'm not going to start the course. I'll just introduce you with a lot of things that you should be knowing. Okay. Should we begin then?
Yes, sir. Sir, I
Okay.
think
Yes,
recording is
please
not
go ahead.
started.
Yeah, it has started.
Oh, now it's started. No?
Okay. The very first thing that all of you should be aware about is, I think the session has expired. Let me relog in. So if you see, this is your LMS wherein you will get all your updates on. And Professor Venki is currently the lead in charge. We all are just helping him to cover all the aspects of mathematical foundation for machine learning. So you will see all the classes running parallelly, right? And here are a lot of things that resources, or all the resources that you need. The handout, you could go through it, you could download, let's say, for example, from here, you could see what is included as a part of the curriculum. These are some of the books that are recommended, but I'll tell you about two more books that you should be, at least if you're not buying, you should go through them. Okay. But these are also pretty good books. Then you have these modules. Modules basically is divided into two parts. First part and the first four lectures that you see, they are all belonging to linear algebra. Okay, and we will get introduced to the concept of vectors, then matrices, then how do we use vectors in doing calculus. If you see here that this particular part, right? Then optimization. So my master's was on optimization. So this is the part that I teach with a lot of passion. So you'll see that will take a lot of time in covering optimization and machine learning, even though life for that matter is all about optimization, right? So machine learning is optimization. So you'll understand all of those concepts clearly in these sections. Then post that you will learn about some of the applications of these things that you have learned up to module 6, like PCA, which is dimension reduction technique, and then you have support vector machine, which is one of the algorithms that we use for classifying data. But these things would help you understand how does maths go along with machine learning. So the very first, so if you have to divide the entire module M1 from M1 to M7, they are divided into two sets. The very first set is all about linear algebra, wherein we will get introduced to vectors and matrices. The second is all about doing calculus using vectors and matrices. Okay. So this is how it is going to be. We'll get introduced to linear algebra in a bit. I'll give you a quick understanding of what exactly it is and how should we looking at it. And because this is the first session, I'll go slow. I'm not going to cover the lecture components, but I would be covering it in a way that you will not even realize that I'm covering lecture one, so that you understand it much better. Okay. Now, these are all the contact sessions that you see. Today's session is meant to cover linear system of equations, but before getting into this, I'll first introduce you the subject itself, okay? And then all the other subjects are divided. So handout is very important for you to understand what we are covering, how we are covering, and what is included in the syllabus, right? So you should go through it. Post handout, there are a few other things which are included on that page if you would have seen, right? So these are the practice problems, Mfml reading and practice problems, right? So a lot of, let me open this up. So when you open it, now this you see that you have a list of topics on the left hand side. Then you have assignment type, whether it's a reading assignment or a practice assignment, which book it is, which resource it is. So you'll be able to search it out, either download the PDF or you should be able to buy that book and do those exercises. And specific questions in that section has been marked so that you can go through the section which has been marked as a practice problem or as a reading assignment, right? So I think Professor Ashwin has done a really good job accumulating all of these things in the last semester. So that's why Professor Venki has thought that we'll be using it and we'll be going ahead with this. But apart from this, this is not everything that you will need. The way I have been doing it in the previous semesters to your seniors is I have created practice documents. So practice documents for your examination preparation. It is an assembly of 40-50 questions, which I feel you should be practicing from your exam point of view. They'll be helping you a lot. It covers the kind of question which has been asked previously in the previous examinations. Plus, it also covers the kind of question that you should be answering or you should be knowing because this entire subject is as important in terms of application, right? So most of the questions are also application oriented. So I'll be sharing all of those things with you. I'll just I see that someone has raised their hand, but let me show you how I have been doing till now. So if you see here, this is your last batch. And in your last batch, what I did was I had created these sections. If you see companion docs, So every lecture that you see as a PDF or as a presentation which has been shared to you, I decompose those into component docs. Now, the essence of component doc is these are easy to grasp uh, documents for you to understand it in 4 or 5 slides or 4 or 5 PDF documents. When you look into it, let me zoom it up so that you can understand what I'm talking about. Okay, so not able to do that here. Now you see that everything is provided in such a way that you can have a good understanding. Sometimes what happens is the content that we are trying to cover in slide, it doesn't becomes very readable, right? So it this document would be good enough for you to get a gist of what exactly is being taught in those slides, and in a language that is slightly more easier for you to understand. Okay, I mean, this particular thing might not be, because initially when you are looking at it, it might not look like very easy, but when you'll go through some of the most important and very difficult to understand concept, you'll understand that this is actually very easy to understand and apply. And these are not very long documents. I call it as component documents because these are just prepared for helping you understand the slides in much easier and better way. This is the first thing, okay, that I'll be sharing with you. Second is, as I was telling you about the examination preparation, it is all going to be slightly tougher because all of us, I also come from the same industry, right? So it becomes slightly difficult to give time to learning, especially during the weekends when we have a family. I understand the complications that we all have. So what I have here is you have examination preparation, and within examination preparation you have practice problems. Okay, so different types of practice sets are there, but these are two different practice sets. If you see practice problems and final practice problems, these are the most important ones. I will, based on whatever has been included new in this syllabus, I would give you all these practice problems to you so that you can keep practicing. So you will see that the practice problem themselves are divided into three modes: easy, moderate, and difficult, so that you get an understanding of how difficult the question could be, how easier question could be framed, and also the applications of it, so that you are able to understand the kind of questions which are asked. Also, you are able to understand the applications from these questions and so on, right? So these are going to be extremely helpful for you. Then, apart from this, when you go back, let me go back. The other important aspect is where is it? Okay, I create these HTMLs, and these HTMLs are the ones which help you visualize things much better. And I have started doing this. So if you'll go to your now, if you'll go to your lecture, I think this is the one, and you go to shared on Teams. I have already created a folder which is lecture_1. And you have three different things here. This is the slide, this is the component document, and when you'll open component document, you'll understand why I was saying it is actually easier for you to go through than going through the slide. If you feel that you have time reading, go through this. This has been written with a lot of efforts. I dedicated a lot of time in making things easier to understand, easy and easier to express, so that we use an example which is easier or easier to visualize or imagine, right? And that's all because we have to understand it from machine learning point of view. So everything is included here in this. Okay, whatever you need to learn, at least from lecture number 1 point of view, is included in lecture 1 companion. Okay, then I told you that I'll be including HTMLs. So this is the important part. These are the HTMLs which I keep preparing. This is what I have been doing ever since LLM was not that mature. But since it is now very mature, I take a lot of help from Claude or Gemini or GPT, right? So if you will see, what I'm talking about is these are the HTML that I keep creating. So if you would be here, you will see that these are pretty interactive, and they will give you an understanding of what exactly it is. And quickly, I'll go through these HTML. These are interactive visualizations that you should be uh, trying out so that uh, you understand the concepts much better. Okay. Now, these HTMLs sometimes will give you an understanding which is far beyond the understanding that are there in the books. So that's the only reason that I keep creating these, and it will eventually help you in a longer run, not only from this course point of view. Think of how you would be utilizing machine learning into your various different industries or various different job roles that you are in, right? So these things will help you in all those aspects. Plus, not only these HTMLs, because I have been in this space for a longer period of time, I created this website, which is what I'll be sharing with all of you. This is what I created almost like around 2.5 years back, but I gave it a lot of new flavors with LLMs. So I asked it to enhance it. It was able to enhance it. Now I'll share it with all of you. Let me share the link. It's called linearalgebra.info. And on this page, or when you open it on mobiles, you will see that you have pretty good interaction available. This is mobile first website. So you can interact and learn about what exactly is a vector, then go to add and subtract vector, use your fingers to interact, see how addition of vectors work, how scaling of vectors work. I will be using these things whenever those concepts are introduced in the class. So I'm just introducing you with the website, saying that this is an interactive place which will give you an understanding much more than what is included in the books, what is included in the slides, because maths is all about the nature, right? So if you are able to visualize it, that is going to help you a lot. Okay. Then you have all the other aspects of it. So this is what I'll tell you today, because this is the most profound ideas that I see in linear algebra, the transformations. So you will get to see these things. Now you might ask me a question why I am doing all of these things. Again, my passion for maths is much bigger than what I do in my daily life. So I have been teaching for a very long period of time, especially maths and mathematical topics. And when you will go through 3B 1B, I think some of you might be knowing about 3B 1B. This has also have added an inspiration to me. So this is a channel on YouTube by an individual from Stanford. You would see that on 3B 1B there are videos which are included on linear algebra. So I think linear algebra 3B 1B. So this is the essence of linear algebra. You will see a lot of, let me pause. You will see all of these chapters included. Okay. On the left hand side, so the videos, and on the right hand side, you have all the topics included, right? So you have span, linear transformation, matrices, 3D transformation, determinant, visualized really well. Okay, so this has gotten me into the space of visualizing the concept better. So this was the reason why I have created the website. And you will see majority of the concepts that are here, they are actually because of the way I got an understanding from those videos, and also from various different types of books. Okay, eventually, all of these things which are included at the top where my cursor is, these are going to be what we are going to learn in linear algebra, starting from vectors till the last, I think this is the 12th, 11th or 12th chapter in your handout, which is PCA. Okay, so we'll be doing all of these things, but this is only about maths, right? So what I have also done is, this is my own website, which is called as animatedml.com. I was able to get this domain easily, but you will see on animatedml.com the same. This is mobile friendly website. You will have topics like supervised learning, unsupervised learning, reinforcement learning. So you will be learning about these concepts in your machine learning classes. And when you will learn about any algorithm, let's say whosoever is teaching machine learning to you, let's say they have taught logistic regression, come over here, animate the thing that you learn. This is mobile friendly, and that's why it doesn't looks really good on this. But when you'll go to neural networks, for example, these are the things on which LLM are also based on, right? So you'll understand it maybe in this semester or in the next semesters. You will understand how neural network acts as a base to whatever AI we are doing. So you can come over here, interact, add neurons, add network, add hidden layers, do a lot of interactivity, then animate the entire process. Okay, so you'll see how machine learning actually works in doing classification or dividing two different groups of data points. This is a red group versus blue group. You will understand all of these things in a bit. It's in the very first class, it might become boring, so I'll not include what exactly it is. You will eventually discover all of these things in your various different classes. But what I'm trying to tell you is, this is a place wherein after you learn anything, come over here, try visualizing those concepts, because if you could visualize those concepts, it means that you have understood them well. Whatever it is, whether it's supervised learning, unsupervised learning, whatever it is, go through it, see if you are able to understand them well. Okay, so this is how the visualization would work. These all these websites will help you. Thirdly, there is another thing which is statistics.com. This is again the third website that I created for statistics, because I told you my belonging to Indian Statistical Institute, and wherein I was taught about statistics a lot. You would have another subject in as Introduction to Statistical Methods, right? ISM, wherein you will be taught about these foundations: random variables, expectation, probability distributions. I have tried giving you an simpler concepts of visualizing these things, okay? But there are various different other things that I'll be sharing from time to time, either on groups or on WhatsApp. Okay, so these are three different places. First, linearalgebra.info, which will help you visualize the concepts that you'll be learning on linear algebra, or every single aspect of it, whether it's a dot product or whatever matrix multiplication, you should be able to visualize them here. Okay, so it's pretty easy for you. You might have already gone through it by now. Since I have already shared it with you. This is the second one, which is animatedml.com, and this is what you will use for machine learning. And this is the third one that you'll be using for ISM. Okay, good. Now I see that someone raised their hand.
Okay, so
Can I ask one question?
Yeah.
Yeah. So yesterday also, I think we were having the same kind of information by another professor regarding the reinforcement learning and this unsupervised supervised learning. So are we repeating the same class, or what's the difference in these two classes? Yesterday we also had later at 10:30, and today uh, you're also teaching the same thing. So
No, I'm
uh,
go ahead. Whosoever
so
is
what's
talking.
the difference in the two classes from yesterday to today?
Yeah, I'll tell you about it. You will have to hold on to your thoughts. See,
Mm.
the difference is we are going to cover mathematical portions. Reinforcement learning, all of these things is what you will be covered in machine learning. Okay. Or there is a subject which you'll be getting introduced to as machine learning. And in your machine learning, you will be introduced with topics like supervised learning problems, unsupervised learning problems. There are two different types of learnings that we have. One is called as learning via examples. The second is called as learning via experiments. Okay. Learning via examples is divided into two things. One, supervised, unsupervised. And then you have learning, well, think of you as a kid, how have you been learning, right? You would have learned by doing experiments. So if someone would have asked you not to touch a knife, you will eventually do that and then learn from it. Or let's say if someone would have asked you to not to touch the ice, you would have only touched it and realized that it is cold. So reinforcement learning is all about that, and this is what you'll be told in the subsequent sessions, in subsequent semesters. Reinforcement learning is also a subject that will be taught in this semester and the next semester. I don't know in which semester it is included for all of you, but it is a topic. I will be teaching, or I'll be covering the mathematical portions of reinforcement learning or machine learning. Okay, so what builds machine learning, the maths behind it. Okay, so from that perspective, good.
Okay. Okay. Thanks.
Oh, hello, sir. So it's Abhishek here. So mainly my question is that, so instead of going through lots of books, can't we have the good resource material of the video? Because frankly, I will not be having so much of a time to read through the books. So if it will be the good videos that we can go through, and then for the practice we can check on those
Right.
books or whatever is there. That's what I
See,
think.
definitely. See, videos is what the very first part of the question that you have asked, and I'll try to answer it in a better way. You will get most of the learning in these 2 hours. This is your first session, but most of what you need to know, you will be learning here in this session. I'm not saying that it is only me who can teach you. You have various different professors, but you will be getting to know about those concepts, understand them, applied side of it. You will be knowing about the applied side and so on. But this session is going to be important for you, so that's why I would want all of you to be present at least, or else see the recording. Second, videos. I understand that take going through the books, it might take a lot of time, but believe me, if you will go through the books, it will be important. Given that you all, and I understand the problem that we are all in, we don't have time, right? These things have been created specifically for those problems. Okay, so videos would help you, and that's why I was telling you 3B 1B linear algebra is good, and even they have included calculus, so it would give you the understanding that you need. But the practice would only come from the books, from the questions, from the things that I'm sharing. You may not be going through the books, okay, but given that, let's say if I start teaching you and you have liked the subject and you want to do something or some research on top of it, then in that case, you would have to go through the books, because I would be only imparting the crux of everything, right? I cannot give you the entire knowledge about linear algebra or calculus in 16 lectures or 32 hours, right? If you have to be on top of it, you'll have to go through the books. There is nothing else that can help you. But from your exams point of view, from your applications from point of view, from learning about how to do machine learning using all of these things, I think these lectures and whatever I'm sharing, this should be good enough. Okay, good.
Okay.
Okay. So don't worry about it. I'm not saying that that see realizing the problems, the pain points that a lot of you, not only you, a lot of people who have had these problems in your previous batches. I created these companion docs because when I went through the slides, I found that it was very difficult for people to understand the mathematical notations even, right? Sometimes it becomes very tedious to first understand the notation and then get the meaning out of it. So these things that I'm sharing with you, they have gone through a lot of revision, a lot of thought process and whatnot. So uh, take it as it is, and whenever you have a problem, you already know that I'm available on Teams, and you can create your WhatsApp channels wherein we can keep discussing. So don't worry about it. at least from the perspective of linear algebra or from the perspective of mathematical foundation, I'm assuring you that you will do much better. So don't worry about anything at this point. Okay.
So, Professor, you will be
So
sharing the companion docs in Taxila or in Teams for us?
Teams. I'll be
In
sharing it on
Teams.
Teams. Okay.
Okay.
And the other
uh,
thing is, yeah, go ahead, go ahead.
Sir, sorry, I joined a bit late, but I just heard you were mentioning about WhatsApp channel. So if there is a WhatsApp channel for this subject, can you let me know, please?
I think some of you would create, and you can also add me there. You can share the link, and I can get added there. So
Okay.
someone can add that and share it in the chat so that we can all get added up there, and then we can start sharing our interest, our our thoughts, and whatever we have the problems in, so that I can get them sorted. Okay.
Yeah. Okay. Thank you, sir.
The other thing that I was telling you is I do not use slides. I generally go by board. So all the things that are there in the slide, I will just get the idea from what is covered there, and then would cover it on boards. And this is the whiteboard which I'll be sharing post we see the MFML lecture one. So I'll be writing everything here, and then post the lecture I'll be sharing all of those things with you, so that it becomes easier to do problems. It becomes easier to help you visualize the concept directly on the board. I am coming from the background wherein we used to get taught on blackboards with white chalks, right? So that's the best feeling of teaching. At least some of you who realize the importance of writing on board, it is immense. It gives you immense satisfaction if you are a teacher, right? So I write like writing on boards, and you will feel that it also might go well with all of you. Okay, this is from resources and how would we be doing. Now, coming back to the course, given that we have already covered 40 minutes of the time that we have to cover on the course or the course material. But now I'll give you an introduction to the subject or overall subject, so that you understand it well before you delve into chapter one or slide one, and then go through each and every topic. See, the maths that you're learning, at least from the machine learning point of view, every topic that you are learning, I told you that it is all divided into two parts. One, you have to understand linear algebra well. Okay, linear algebra is the base to everything. Second, you have to understand calculus well, because calculus would help you understand optimization. So if you think about why we are doing calculus, think of in machine learning, you are trying to build a model, a very accurate model. So an accurate model is the model which minimizes the error, right? And minimization is all covered in optimization, and optimization is all part of calculus. So you'll have everything is connected. You will have to learn all of those things. And now, why is linear algebra important, right? Where does linear algebra fits in? See, everything that you see in machine learning, every data point, think of it as you're trying to predict on the prices of houses, right? So let's say that there is a house, and let's say that it's a 2 BHK house, right? 2 BHK. Let's say that it's a 2 BHK house. It doesn't seems like a 2 BHK house. Let me let me make it a 2 BHK house. So let's say that it's a 2 BHK house. Now, given that you know about its square fits, let's say the square fits of the house is 1800, and let's say that the number of rooms are two. Okay. Now, this as a data point for you, you know that this particular house is of 1800 square feet, and it has two rooms in total. This, if you have only one information, okay, this particular information, let's say either square feet or the number of rooms, it becomes a scalar unit. It becomes only one piece of information that you have. When you have a list of numbers, when you have two specific numbers, and you, let's say you would want to plot it. Let's say that on my x-axis I have square feet, and on my y-axis I have number of rooms the houses have. Okay, now let's say for example you have 500 here, and then you have 1000, 1500, this is 2000, right? So 1800 would be somewhere here, right? On this, on the x-axis. Similarly, let's say you have one room, two room house, three room house, or four room, and so on. Because it's a two room house, you basically are saying that this is the point. This point, when you see it from the coordinate axis point of view, it could be seen as a vector like this, right? A vector has two things. One, the length, and also the orientation with respect to some place from where you are viewing it. So it might be inclined in a northeast direction or northwest direction or whatever, but you could see that there is a particular direction assigned to it, right? This is the direction, and it has a length. So vectors are the dimensions. When you have more than one dimensions, it moves from scalar to a vector, and a vector could be represented like this in a two-dimensional world. Similarly, a vector could be represented in a three-dimensional world like this. Think of it as, let's say I have had square fits. I don't know who is there. Okay, sorry about that. So let's say square fits is there, and then you have number of rooms, and then you have the prices, house prices as well. Now let's say that this is where the house lands. This is right now a three-dimensional vector. You see that this is a three-dimensional vector which has three things. One, 1800 square fits, two rooms, maybe 2 crores. Right. So it has three different units attached to it. Right now it's a three-dimensional vector. So a vector, what exactly is a vector? Vector is something which, from physics point of view, vector is something which has a length, and also it is pointed in some direction, right? So something which has magnitude and direction. That's what we learn in physics sense. But from machine learning point of view, think of it as you have vector, right? You have one vector which is like 1800 square feet, two rooms. Then there could be another vector which says another house is 2400 square feet with four rooms. Then you have another house with, let's say, 1500 square feet with three rooms. Okay. You could have many number of houses in the same area. Now, let's say that you are working on a problem wherein you use these two dimensions. That the first dimension is the number of square feet that you have. The second dimension is the number of rooms that you have. Okay. And then you try to see what is the price, house prices of each one of them. So this is a one-dimensional unit, or let's say only one number, a scalar number, right? Let's say, for example, this is 2 crores, this is 3 crores, this is 1.5 crores, and then so on. So each one of them are attached here, right? So let's say that a house which is 2400 square feet, okay, and which has four rooms, it is of 3 crores. A house which is 1800 square feet and two rooms, it is of 2 crores. Now, given that you have a new house in place, let's say there is a new house which is 3200 square feet and has six rooms. Someone comes in and asks you, how can I predict the house price using these two information that I have? Now, if you think about it, this becomes your historical data. All of these houses, this becomes your historical data. Let me write it as HT. And what we do is, in the entire machine learning, we use this historical data to learn from whatever relationship that we can build between the prices. Let's say this is price and square feet and the number of rooms. So we'll have to learn a relationship between these. But if you think about how this entire information gets captured, right? If you think of this entire information get captured in a two-dimensional representation. One, has number of rows attached to it. The rows are, let's say this is house number one, this is house number two, this is the second row, this is house number three, this is house number four, and then so on. There could be multiple number of houses. Then you have dimensions, as in what is that feature that you are evaluating those houses. You could have square fits, the number of bedrooms it has, whether it has swimming pool or not. I mean, uh, let's say that it has swimming pool. Let's say that these are the three different things that has been added. Let's say a house, 1800 square feet with three rooms. It doesn't have a swimming pool. What is its price? Let's say we have a representation for price as well, 2 crores or 3 crores, and then so on. Now you see that this entire vector, this is the first vector that we had. This is the second vector that we have. This is the third vector that we have. This is the fourth vector. All of these vectors are all arranged in a nicely looking two-dimensional fashion, wherein first dimension is the rows, second dimension is columns. This entire assembly is called as matrices, right? So this is called as matrices. Now, when you have a matrix wherein you have only one column and multiple rows, these are called as vectors. These are vectorized. So if you think about it, you can also, these prices, house prices, you can actually also translate it in this way. One house was of 2 crores, second house was of 3 crores, and so on. So these are arrays of numbers, and arrays of numbers are called as vectors, right? So this would be called as a vector, while this particular thing would be called as a matrix, which has two-dimensional information in it. Anything which has one-dimensional information in it, you would have called them as vectors. One-dimensional as in only the one dimension that you have. Anything which has two-dimensional information or more than two-dimensional information in it is called as matrices. Now, how does linear algebra helps you with all of these
Sir,
things?
I have a question. Sir, I have a
Yeah,
question.
yeah, go ahead, go
Yeah.
ahead.
So just want to ask, because everybody start with vectors and matrices, I'm not able to visualize how it relates to vector and matrices. Vectors, I understand. Matrices, I understand as a layman, but I cannot link how it is linking from the real world data to this. You're saying house prices, the features of the house, like 200 square feet or three rooms or 2 crores, 2 BHK. How do we understand maybe in another uh, way? I have a 360 degree space. I have many, the XY axis and all these things. So can you tell me in a way that I don't know, can understand more?
Okay. See, there's the very first thing is you you get that essence, let's say. When you see a house, okay, when you see anything for that matter, let's say a flower or let's say any other thing, whatever you visualize, you see features, right? You features out of it. You see a house, you see features of the house. You see an individual, you see features out of those individual. You see whether they are smiling or not, whether they have hands, how many hands, with how do they look like. You see a flower, you see what is the color of the flower, what how does it looks like, what how does it petals looks like, and so on, right? You understand everything from their attributes, and these features are called as dimensions. Okay, now understand that vectors and matrices are a way of representing these dimensions in a mathematical way. Okay,
Okay, understood. Okay.
whatever you see, for example,
Mm.
let me make it more profound. Let's say that I write a word, I love my country, or I write a sentence, I love my country. Now, for me and you, it becomes very obvious to look into the sentence and say that what exactly it is. And someone is very passionate about their country and they have written about I love my country. But if you think about it, whatever I have written out here, okay, computers, some of the computers every computer they'll be able to understand right now because of the LLM and all the things that happens beneath the computer systems. The way we represent all of these information is via features. Okay. And those features are called as dimensions. And those dimensions, think of it as if I have to convert this into a numerical language, into something which is more numerical, let's say that I want to convert this into a mathematical language which computers can understand. Let's say computers do not understand text or raw information, Hindi or English or Bengali or whatever, right? They do not understand that language. What they understand is maths. Then they understand numbers. So what we'll need to do is to make them understand that someone has written this text. You'll have to first convert them into numbers, and a very well representation of numbers are called as vectors, because vectors are an array of numbers. Now, what you can do is you can use the same text and convert it into a numeric vector and say that, let's say that how many number of words it has, okay, and how many number of vowels it has. For example, in this particular sentence, I have 4 words, and let's count the number of vowels. 1, 2, 3, 4, 5, maybe let's say 5 or 6. Okay. Now we have represented this word, or the sentence rather, which was I love my country, into using these two representations. Okay. Or basically these two dimensions, the number of words and number of vowels it has. So you have a representation which can be used to make the computer understand what exactly it is. Similar way, this is a simplest decomposition of a text into vectors, right? So what you have done is you have decomposed it into an array of numbers, which is what we call as vectors. Now, what we do is to make the computers understand whether it's an image, for that matter, or it's a text, or it's a historical data that I was telling you about, let's say square fits and the prices of the house. All of these things, they get converted into, all the features get converted into numbers, whether it's a text information or it's a restructured information which is in square fits and prices, or it's an image, for example, for that matter. You would convert all of these into numerical representation. Okay, let me write it as NP. These numerical representation is what your intermediate representations are. And then you use this intermediate representation to talk to the system. Right now, whenever you prompt on LLM, what LLM does, it breaks down your text into a vector. We call them as embedding, right? And these embeddings is what they use to understand what you are telling. These are numerical representations. So these vectors are nothing but some numerical representation such that the systems that we are communicating to, they understand it. Good? Yes, no?
Sir, so hello.
Okay,
Yeah, go
sir.
ahead.
Okay.
Sir, then here when we are using the matrices, like in this example which you have given, I love my country and houses and all.
Mhm.
So where matrices comes into picture.
Matrices is when you have many vectors. Think about, let's say you watch a lot of things on Netflix, right? Let's say just like you, there are many number of users who are using Netflix. Let's say you have given a lot of data to Netflix. Maybe, and let me use another example. Let's say that you you use these cab providers like Ola or Uber, right? Or Uber. You might be traveling, let's say 50 times in a month, and might have spent, let's say that there are only two dimensions, might have spent 20,000 rupees, okay, on these 50 travels. Someone else might be there. Someone else might be there. Let's say that there is another individual. This is you. This is A. There could be another individual B, and B could be more frequent in travel. B could have traveled and 1800 times and could have spent 50,000 rupees. Okay. So to represent all of this data, you can represent them either as a vector or as a matrix. Okay, so when you club together this information, wherein you have dimension as rows representing each individual. Let's say this is individual number A, this is individual number B, then you have individual number C, and then Ola or Uber would have millions of users, right? And all of these users are represented with these dimensions. Let's say how many number of trips that they have done and the number of amount of money that they have spent. Okay, now let's say this is 50, this is 20,000, 20K, this is 1800 and 50K, and then so on. Now this is the information that you have in matrices. This is what you use as matrices. Now the question that you should be asking is, how does all of these things relate to machine learning? Think of it as, what you'll be doing is, let's say there are two dimensions, and I'll give you the concrete example of why linear algebra is so profound. So right now you have two dimensions, the number of trips, amount of money, right? So what Ola or Uber does is they divide all of you into brackets. Let's say, for example, you are here. This is user number A, which has done 50 trips, 1800 rupees, right? There would be a lot of users who might be doing more number of trips, but spending lesser, because that's how you see all of these users that you see here in green color. They are not spending a lot of money because on the y-axis they are not on the higher side, right? Then there could be a lot of power users who are spending a lot of money and they are also doing a lot of trips. Now for you, this is the cohort that they do not want the users to be. What they do is they give you push notification saying that do more number of trips and get 50 rupees off, right? Because they want all of what they want is all that they want is to move you from this cohort to this cohort. Now this is what is called as clustering. This is what you will be eventually learning about. So what they do is they use this information in matrices and then apply machine learning on top of it to discover some information that can give some business context to it. And then using those business contexts, they try to do whatever they would want to do with that data. This is a simple example that I'm giving you. So what you start with is, you start with a vector which is only representing one user, maybe, right? This is one example. When you have matrix would be representing multiple users. Then you will use those metrics to learn from it. You will be doing machine learning on top of it. Good? Yes? No?
Okay,
Okay,
I,
so
sir. So
what I
there,
means
understand.
vector.
There is some discussion going on
So
chats.
means
Can
a
you clarify?
vector is only for one dimension, and can be multiple dimension. Like
Yes.
as you said that first one, 50 and 20,000 is representing only one person. So it's a vector.
Right.
But if we do for multiple, then it's matrices. Okay, sir.
Yeah.
So just want to repeat, sir, what you told. Object has features. Features has dimensions.
Mhm.
One object is represented by one vector.
One
Suppose it
vector,
has 10,
right?
yeah, it has 10 features. Suppose age, gender. And if we
Mhm.
group them in one, like we are analyzing 10 objects, like 10 people. So we will create a
Matrix.
n order a matrix about it, like
Mhm.
an order. And
Mhm.
the dimensions are equivalent to the number of columns, right?
Columns. Exactly. That's right.
Columns. Okay, sir. Okay, sir. Thank you. I think I got it now today. Yeah, thanks. Thanks.
Sir,
Very interesting. Yeah, thanks.
there is some discussion going on the chats. Can you clarify those people?
Yeah, yeah. Which one are you referring to? There is so
Basically, my
much.
understanding was each vector is a set of similar uh, data type. Like you have age, all values should be age in a vector. So in that case, in a matrix, each column is a vector. One column represents age, one column represents square foot, another column represents probably weight. Now, when you combine them together, you create a matrix. In that case, each row represents an observation. So a person of this height would be so heavy. Person of this region would be having so much income, something like that. So in that
Isn't
case,
go ahead, go ahead.
in
Sorry.
that case, each vector is a column, not a row, right? In a matrix.
See, that's why the concept of transpose is there. You will be learning about all of this, but majority of the things that you have told is correct. There are some things that I would want to tell you. See, vectors are not only one dimensional thing. Okay, one dimension as in you have a vector only of age. What you have, what, and let me correct your understanding there, because when you represent anything which has multiple dimensions, let's say for example, whatever it is, when you have only one particular observation, let's say that observation is, let me think of, let's say about this particular class. Okay, you are making an observation about this class, number of students who are there, and the entire duration of the class. Now you have two dimension. You are representing the number of students and the duration of the class as one of the vectors. Say there is this class currently going on, then there are other professors who are there who might have lesser students. The currently in this class there might be more students, and then there could be another professor who is having some few more students and might be running for a longer duration, right? So if you think about this particular, all of these things, okay, all of these representations, they are all vectors, and these are having two different dimensions. So we use different dimensions to define any characteristic of whatever observation that we are making. So observation is a data point, but we can define that data point using different ways, right? So think about it as you have, let's say that you have a MacBook. You would want to define a MacBook using different features. Those features become dimensions. Those dimensions are what is the color of the MacBook, let's say color, size, RAM, or whatever. So these are different things, but your MacBook is one, right? So you have one MacBook. It's your MacBook. Let's say it's yours. Your MacBook has a gray color. Size is, let's say, 14 inches. RAM is, let's say, 32 GBs, and then so on. So all of these are different dimensions, different features. But what it describes, it describes your own computer, your own system, your own MacBook. It's a one entity. Okay. And this is a vector which describes your one entity. Okay. When you have
So,
too many entities described, then it becomes a matrix.
uh, so sir,
Understood.
just
Yeah.
just just one.
Yeah, go ahead. I'm not able to hear you out, whosoever was speaking.
Can you
sir,
hear me now?
Yeah, yeah.
So what I was concluding is, whenever we talk about vector, we are just talking about one of the feature or characteristic or aspect of that object in discussion, right?
When you're talking about a single vector, you are talking about one object. That could be a much better way. Let's say
Okay.
one tweet, one movie.
One. Okay.
so sir, can we say that if we fix the RAM and we compare all the different version of that computer like Pro or X, some basic model. So in that case, it's also a vector, right?
Yes, yes, definitely. Let's say there is a computer A, there is a computer B. Pro version, let's say mobile phones, it's basic versus pro, and basic would be represented. This is a numeric representation, but in, let's say, in visual representation, you have number of RAMs and, let's say, the size. So you have one which has, let's say, 16 GBs of RAM, and let's say size is 14 inches, so it is here. Someone with 32 GBs of RAM with size slightly more, it would be, so let's say here. So this is the second vector that you have. This is the first vector you have. And then the interesting part is not this. The interesting part is when you are seeing it, let's say these are all the visual representation of the vectors, right? When you have visual representation of the vectors, what you do, let's say you have all of these vectors, many vectors. Then you want to combine in a way that which vectors are actually closer to each other, which vectors are similar. Obviously, these are all similar types of books, similar types of computers, similar types of houses, or whatever you are. That's how things go together. Let's say whenever you visit Amazon, they find you similar things, right? Similarity is when things become similar, when the vectors that they represent, that are used to represent them, they are actually closer to each other. Then they becomes very similar to each other, right? So right now we are looking only at 2 dimension. Think of it as, while this is the most important aspect that you should be understanding. Right now we are talking about 1 dimension, here 2 dimension, and then we can stretch this idea up to 3 dimensions. But think of it. This is 1 dimension, this is second dimension, this is third dimension. This could be the number of RAMs of the laptop, the number of size of the laptop, the color, whatever. When you actually increase this idea to n dimensions, many dimensions for that matter, when n is many, then it becomes very difficult for you to visualize, right? You cannot visualize something which is more than 3 dimensions. You cannot visualize 4 dimensions for that matter. But linear algebra, linear algebra, it helps you do maths on making this concept more abstract.
So can
Okay.
we say that n is 360 here, 360 degree, or it can be n like
And could be
beyond.
anything. And it could be 16 dimension, it could be 30 dimension, it could be 100 dimension. Okay. And could be anything. The number
So
of
the
dimensions could be
sphere,
any.
sphere, we can think of it as a sphere, and the center point is the where we can make many vectors in any direction to represent each feature or attribute of
A
the.
sphere is still 3 dimension. I mean, you have a
Oh,
point in space which is only 3 dimension. So when you
oh,
have anything which is n dimension, let's say for example you have a car. Okay, I'm just telling you about. Let's say the car has multiple dimension with the weight of the car, the horsepower of the car, the mileage, whether it is automatic versus manual, and then so on. Right now, you have 4 dimensions. Now, you cannot visualize these 4 dimensions, but you can do maths. You can actually, you can uh, enhance the idea of vectors. You could use these 2 dimensions to represent it in two-dimensional word. You can use these 3 dimensions, weight, horsepower, and the mileage, let's say mpg, mileage per gallon. So you have these 3 dimensions that you can visualize, but as soon as it goes into 4 dimension, you cannot represent them into a visual chart, right? Into a coordinate system. So then 4 dimensional coordinate system is what you cannot visualize. 5 dimensional coordination, if you have added one more dimension to it, think of it as you have added a vector. Let's say this is car number one. This is your car. The
mm,
next the next entry in the matrix is your neighbor's car, car number two. Now you are evaluating both the cars, and you have too many dimensions to be compared for both the cars, right? So you have car number one, which is evaluated with, let's say, 7 dimensions. Same car number two with 7 dimensions. Now you cannot visualize them, but you can do maths with it. You can
oh,
use the same idea of vectors to compare whether the vectors, let's say the numbers look similar to or not, right? Let's say
mm,
here you have weight as 2 tons. Here you have weight as 3 tons. Here
mm,
horsepower is 1600 versus horsepower 2000. Mileage, let's say 20 versus mileage 32. And this is automatic versus manual. Now you have all of these features being compared. So you can do maths with it. You can extrapolate your logic from 1 dimension to 2 dimension to n dimension, but you cannot visualize more than 3 dimensions. You can
oh,
do maths with it. So linear algebra, this is what I tell a lot of students early. Linear algebra is a way of doing or visualizing maths in 100 dimension, more than 100 dimension and dimension. Linear algebra is basically the maths build on abstraction for n dimensions. Okay, you can do all the maths even without visualizing them using n dimensions. Okay, so that's what is linear algebra. This concept is good
okay.
till now.
Sir,
Yeah,
Yes,
yeah,
if
I
we
think quite
sir, if
informative.
we
Yeah.
want to
yes,
add the vectors and
yes,
the
it was good.
scalar, then how we will add?
Okay, this is where I was telling you about when you go to uh, where is that linearalgebra.info, right? So when you go to, no, this is the newest version of it. So let me go to the website. Okay, so go to vector section. Okay, now you see that there is this vector described with 1 dimension. represented here, the other dimension represented here. When you will go on the mobile, you could use your fingers to represent it. But when you have to add vectors, basically you are talking about two different vectors, right? So you see a vector and b vector. When you add the two quantities together, let's say the x dimension of a vector, the x dimension of b vector, add them, and then y dimension of a vector and y dimension of b vector, add them, and then you get a plus b. This is a visualization of how does it looks like. But eventually, if you think about vector addition and vector subtraction, let's say you have two different vectors numerically represented in maths, two vectors, let's say you and me. Okay, you might be 25 years of age, I might be, let's say, 35 years of age. You might be having an experience of 5 years, I might be having an experience of 10 years. Someone might be even much more of experience than me. So when I have to compare you versus me, you could easily see that there is a difference in age, there is a difference in experience. But when you have to add both of these, you would get what, 60 as combined age and 15 as a combined experience. So this is a plus b, you plus me, represented via this new vector 60, 60 and 15. And this is what happens. Let's say you have a vector here. Okay, this is you, and let's say there is another vector here, this is me. When you combine y and m, you might get a new vector here, which is y plus m. Okay, so how have you added? You have added the first dimension, and then you have added the second dimension, and then you have got a new vector. So all of these things are important. Addition of vectors, subtraction of vectors are important because these are the things on which, let's say, you have numbers, you add numbers, you scale numbers, you do a lot of maths with numbers, right? All of the things that you have learned in maths is all about adding, multiplying, subtracting, then dividing. The same concept applies to vectors as well, and this is what you are going to learn next.
So, sir, can you tell me one use case of it?
The use case is let's say, for example, if you would want to think of two different let's say there is an image. Okay, I'm just telling you
Yes.
about very vague concept. Let's say that there is an image of flower. Okay, the flower, the image of, or let's say that the image of flower has looks like this, and then it has petals like this, and then so on, right? So let's say that this is flower. It doesn't looks like the flower though, but let's say that it is a flower. So now when you actually distinguish that into two different images, let's say on all the image enhancement libraries that you have, what they do is they divide your image into different color spaces. Okay, let's say that this is one way of representing how does the edges look like. For edges it would look like this, right? Let's say that this is how it looks like on the edges point of view. And then the other representation could only find out the colors in it. So let's say this is how the colors in the image look like. Okay, and this is what you will eventually understand. This might not be the class to help you understand this, but when you combine these two things, you eventually get this entire image, right? When you combine the corners, the outer layer plus the colors, you get the entire image. What happens is, if you think about the image, it has the vectors represented. An image is nothing but a matrix of pixel values. So what you're doing is you're adding two different matrices to get a new matrix. Now some of you might not have that idea of how is an image represented as the matrix of pixel values. So I'll have to first cover that, but think about it. Just for the sake of understanding, you have represented an image or divided an image into two different representation. One only captures the corners. Okay, the other captures the colors. Now, if you add them together, then only you get the same as, let's say, when you have a signal in place, right? Let's say that this is a signal. You could divide the signal into two things. One, the actual signal, and the error, which is there in it, the error part of it, right? So this is the signal, actual signal, and this is the error. So you could divide the actual signal into into its the core signal and the error part. When you add them together, you actually get this the core signal, right? So this is a signal which is vectorized numerical representation for signal. This is the numerical representation for error. When you add them together, you actually get what is your actual signal. So there are distortions when you decompose your actual signal into two different pieces. One, the actual strength of the signal, and the error part in it. So then you get to see both of them. When you add them together, you actually get the same signal, right? So this is how the vector addition also works. Okay. Now coming back to more profound idea today, and this is I would generally take gaps. This is the first class. I'm not taking gap for the first class because I had to cover a lot of things. And now coming to something that you have already learned. Some of you have already got into the introduction of some of these things like
Uh,
determinants. Right.
Good morning, sir.
Good morning.
Sorry, I have joined right now. So may I know
Okay.
which topic right now you are covering? I mean to say.
We are covering mathematical foundation of machine learning. I'm so sorry that
Mhm.
you had to join late, but try joining little earlier. I mean, what we have covered a lot of portions of it, but what you can do is you can go through the recordings. We are covering right now the essence of linear algebra. We are just trying to demystify everything which will help you go through lecture 1 to 16 in the entire linear algebra so that you can understand linear algebra from the core. Okay, so we are just trying to
Sure,
understand what exactly is there in linear algebra. Okay,
sure.
okay. Now you,
Sir, I have a doubt.
yeah, yeah, go
So
ahead.
when you took the example of that age and experience thing, so at least like both the matrices or vectors, they were representing the same columns. I mean the same features. But when you
Right.
take an example of that flower, like first one is representing boundaries, other one is representing color. So like how it makes sense to add two matrices which are having different characteristics. Uh,
See, you you taken it. You have taken it as two different dimensions. Let's say, for example, when you have an image, what happens is you have pixel values. And pixel values are what? Pixel values are color intensities, right? Pixel values are just color intensities. Now, I'll not get into red, green, and blue color. This is what in your third lecture I'll tell you about how does everything works together. But let's say that you have an X-ray image. X-ray image has only two colors in it. One, uh, either it would be represented as a gray color or let's say black color, or it would have white color in it. An X-ray image has only white and black portions in it, right? So let's say that it's a, uh 12 pixel image. Now, 12 pixel image, what do you mean by 12 pixel image? Today we have camera phones which captures 50 megapixel image, right? Megapixels, which have an image of 50 megapixels or 100 megapixels. These are the kind of cameras that we have in our phones today. But think of that you have only a photo which has only 12 pixels. When you distribute these 12 pixels into rows and columns, what you might see as, let's say, the height of the image is it's more of a longer image than a wider image. So in that case, the number of rows would be more. So let's say you have four rows, first, second, third, and fourth. So this is the first row, second row, third row, and fourth row. And you have three columns. These are the three columns, first column, second column, and third column, right? Now, pixel, because it's an X-ray image, it would have only two colors to it. One, either a black color or a white color. Now, a black color intensity is represented as 0. White color's intensity is represented as 255. Okay. What happens is, let's say there is a white ball here in this X-ray image of a white ball. Okay, so or let's say that it's a black ball here because I have colored it in black. So let's say that it's a black colored ball over here. Okay. Now, given that it's a black colored ball over there in the middle, all the pixels that you could think about in this image around black color it would be 0. So what would happen is the central would always be 0 because this, if you divide this entire image into these four regions, you will see that these are the region or these are the boxes which will have almost 0 as pixel in intensity. These are bright regions in the image. So it would have 255 around, or let's say 200, to 180, 220. These are the pixel values. Let's say 200, 200, 240, 210, 220, 240, and 210. Now this is a representation of color pixel intensity. Similarly, when you device you when you capture the corners in the image, the corners are also pixel intensities. It's just that these corners would be represented there, nothing else. Okay. Now in that case, you have three columns, you have four rows. In that case, you would have, because majority of the portions are white, they will all be around 200, 200, 200, 200. Let's say that this is a slight edgy area which is black, so it is some around 110. This is 110, right? This is, let's say, 90. This is 40. This is 200, 200, 200, 200. Now you see that both the things, this was a color, this
Professor,
was,
can I interrupt?
this is
Sorry.
gray. Yeah,
Hello.
right.
So, I think we are covering just one topic for last 1 hour. So,
Yeah, Professor,
yeah, I
like
mean, maybe you
I
can,
feel
you
like
can,
we are
you,
covering the same session for some past 1 hour.
yeah, well,
We are staying the
okay.
same line of vectors. So I
Yeah,
feel
yeah.
like
So
maybe I don't know,
maybe,
like other people's what they are thinking. I feel like it's like way too much we are spending time. I would recommend like you can mute everyone's mic. Maybe like we can have a doubt session around like 10, 20 or something. Maybe people can clarify if they have any doubt. No, I'm not sure like how other people are feeling, but I'm feeling that.
Okay,
no, no,
see,
see,
Yeah,
this
totally
is
agree
this
with
is
that.
no,
I
no,
would
no,
Yeah,
say,
no.
I would
completely
say,
agree. We
Professor,
are
I
here
would
for
say,
MTech.
Professor, yeah, once again. Professor, I would say it's better you recommend your course. I think you have already, a course on our e-learn portal, right? Takshila now, like zero level or something, right? I think most of the thing is already covered there.
Is it the same course that you have gone through?
Yeah, the zero level. Yeah, zero level.
Oh, okay,
Yeah,
okay.
we went
Oh,
through it.
okay, okay. Okay.
Yeah,
I
a
don't
few
know.
of these
I
scalar matrix, these were covered there, sir.
okay, okay. No,
So
no,
probably doubts we can
right.
cut short cover
See,
later. Yeah.
I understand that. I understand the perspectives that you all are coming in. This is a first class, okay? So don't worry about too much of getting dragged. I'll definitely do all the suggestion that you have, and this is how we go about it. First class is what breaks the ice for all of us. I mean, it becomes slightly difficult for all of us to understand. Some of you might be feeling that we are taking too much time dragging the same concept, but think of all others who are there in the group. They are possibly going through it or learning about it, coming from various different backgrounds, not as good as you. So you have to be a little. I'm just saying that because this is a first class. I can understand what you're going through. Obviously, it is repetitive, but for some of us who are not that good as you, it becomes easier for them to understand it in repetitive manner. From the next session onwards, obviously, we are going to mute all of us, and then what I generally do is I cover the entire session in, let's say, 1.5 hours, and then I'll give time for doubts so that everyone can ask questions in those time. So this is what we'll be doing. But for some of us who have not been introduced to all of these things in the classes, I just wanted to help them understand. But anyways, I'll keep that suggestion forward. I'll mute all of you. Let's do this. Let's have this uh, covered in next 20 minutes, whatever I meant to cover, and then we can come back to the discussion mode. Okay. So all of you have gone through the topics. You said that you have already gone through determinants. This is what I wanted to cover. And given that you have already gone through determinants, firstly, let me ask you, what do you understand by determinants? You can type there because I have muted you. What do you mean by determinants? What exactly is determinants? Fine, I have no idea. Scalar value of matrix, no idea. No idea about it. Isn't that you have learned about determinants in your schools and colleges? This was told to us in our schools at least. Scaling factor. Someone wrote a scaling factor. Scaling factor for what? Good that you know about it. What is that scaling factor? It has been 20 years. Okay, let me give you a concept of the entire linear algebra in this next 20 minutes. Okay, what exactly are determinants or ranks or inverses that we have computed and everything. Okay, see, for understanding the concept of determinant, let me first tell you that you are all learning linear algebra. Okay, and linear algebra, there is the reason why it is called as linear, the linear part of linear algebra, why it is called linear algebra, why it is not called as non-linear algebra. The very first thing that you need to understand is every single thing that you do in linear algebra scales linearly. Okay, so there is a linear part, which is what you would see. You can represent any equation for that example. Let's say that you have a linear equation. Linear equations are like this: 2x plus 3y is equals to 4, or let's say x minus y is equals to 8, right? In that case, let's say these are the two equations that you have. These are both of them are linear equations. Now, if I ask you to find out the values of x and y, you can do substitution and then find out what exactly is x, what exactly is y. But just for a moment, think about how can we represent this into matrices. Let's say we have a matrices of coefficients, and we write the coefficient of x and the coefficient of y here. The coefficient of x in the first equation is 2. The coefficient of x in the second equation is 1. The coefficient of y in first equation is 3, and this in the second equation is -1, right? Now, what happens is you multiply this entire matrix with a vector x and y. These are the values x and y can take. And then you get an output which is 4 and 8. This is basically the mathematical representation. This is more vectorized representation, right? So this is a matrix notation that you have already learned about. In matrix notation, we call this as a matrix A. This is called as a vector x. Okay, and then you on the right hand side are seeing a vector y. So let me call it as ax is equals to b, or vector b. Think of it as a matrix A getting multiplied to vector x, okay, pushing you to a new vector b. Think of it as, again, getting back to the basic. This equation is more profound than any other equation that you will be seeing in linear algebra. Why I'm saying this is because think of A, any matrix A. Okay, let's say that 1, 2, 3, 1. Okay, this is the matrix. And let's say that if I multiply it with all those who have gone through lecture 0 and who were dictating about that they have learned everything, they do not want to waste the time. Tell me what is the matrix multiplication that you'll be getting as a product of these two getting multiplied. This is matrix 1 on the left hand side, which is 2 cross 2. This is 2 cross 1. What would be the output of these two? The output is 2 cross 1, which is right. But what would be the values? What would be the values in those? 10, 10, right? And so you have 10 because you will multiply 1 with 2 and then 2 with 4. So 2 plus 8 is 10. Then similarly, 3 into 2 is 6. 6 plus 4, 10. So you got 10. Now understand this visually, what exactly is happening here in this part. Okay. What you have is you have the dimension. Let's say that this is one dimension, and you are representing the first vector as 2, 4. Okay, let's say that this is 1, 2, 3, and 4, and let's say that you have up to this is stretches up to 10. Okay, similarly you have 1, 2, and then 3, and then 4, and then it stretches up to 10. The initial vector was 2, 4, maybe here. Okay, think of it as this is that position 2 and 4, right? So basically you have the first vector here. This is that position of 2 and 4. This is that vector, the first vector A. Now, after getting multiplied to the matrix, it is getting dislocated to a new position, 10, 10. Okay, now this is 10. If you would plot it out, this is 10, this is 10. Basically, this vector is getting shipped to a new location. This location is B. Okay, now after getting multiplied to a matrix A, let's say that this is, let me write it as vector X and B in the same notation, because I said AX is equals to B. So vector X is what you have here. Vector B is what you have here. What is happening? When you multiply matrix A with the vector X, it gets dislocated to a new position, right? So the vector is moving to a new position altogether. So there is a displacement which is happening. Think of it as, now what kind of displacement could happen? Think of it as a rubber sheet of paper you are holding in your hand. Okay, there is this vector which is placed here. How come this vector could get to a new place like this? Let's say that the only way that you can do is, when you think about it, the only way you can locate or ship this vector to a new position is by stretching it. By stretching this rubber sheet of paper, or applying some force, right? So in a way, this is what you should be learning. In a way, when you multiply a matrix with a vector, you get a new vector. Matrix could be seen as forces, right? Force which dislocates vector from one position to another position. Now, what happens is, when there is a matrix which gets multiplied to vectors, they produce a new vector. And because there are certain forces which are getting applied, this is your input space. Let's say that this is your two-dimensional 2D input space. The entire 2D input space is getting transformed. Some sort of transformation happens in the entire input space. So the input space can get stretched like this. Let's say if I stretch it in both, let's say if I hold this as a rubber sheet of paper from these two sides and I stretch it, and the entire page would stretch like this. It may stretch like this, right? So let's say if there is a vector here, this way it get elongated like this. It would get elongated just like how I have represented this vector. So initially it was at this position A, now it has moved to a new position B. Similarly, let's say, for example, if you stretch it and diagonally, then let's say that there is a vector here. If you stretch it diagonally, in that case, the stretching could produce a new transformed space which looks like this, right? The stretching would produce a new vector. This is your new vector, right? Now, in the entire transformation, similarly, you can also compress it. Think of it as you can compress or you can rotate it. Let's say that this is this vector. You apply compressing force from all the sides. Okay, what would happen? It would get compressed into a smaller size, and then in that case, this entire vector would become smaller. So let's say this is A position. You have now moved to a new position, B position, but the entire vector has got compressed. Now, you could also rotate. You can, let's say this is a vector, and then you rotate it 45 degrees. The entire region rotates. In that case, the entire vector, which was here, it got rotated like this. Right? So this is a 45-degree rotation. Maybe this is how it looks like, 45-degree anti-clockwise rotation. So there could be a stretching of the space, shrinking of the space, rotation, rotation. These are the basic types of transformation which can happen because of the matrix. Matrix A can apply these types of forces: stretch, shrink, rotate. Basically stretch or compress or rotate. Now these are the type of transformation it does. Now because of these transformations, what happens is, when you look into input space, think of these as the grid lines. Grid lines as the numbers that you see on the x-axis. Let's say that this is 0 line, this is 1, this is 2, this is, and so on. This is -1, this is -2. Similarly, you have y-axis, the grid lines, right, parallel to y-axis. So if you think about, this is your 2D space, two-dimensional space, and what you have here is, you have the area which is enclosed within the grid lines. Because of the transformation, this area within those grid lines, it gets changed, right? So let's say, for example, you are stretching it by applying horizontal forces, okay, from both the sides. Let's say I apply force in from these two sides, this side and this side. It will get stretched like this, the way I have represented here. Now there would be gaps in the lines parallel to x-axis. There would be more gaps between them, but the lines which are parallel to y-axis, there would be lesser gaps, the same gaps, right? Because we are applying the same sort of force. So let's say this is how it looks like. Now you see that this area has translated to a bigger area, right? So the area which was A here, it has got changed to B. So this entire change in area, now think of it as here in the grid lines are parallel and equidistant. Here also the grid lines are parallel and equidistant. This type of transformation is called as linear transformation. So linear algebra is all about linear transformations. Okay. Now when you do linear transformation, then the entire area would change. Hence the area in the grid lines, the area enclosed in the grid lines that change. The amount by which this area changes is called as determinant. To help you understand this, see here on the page that I was showing you, go to transform page, okay? And you have these matrix element. Say this matrix, right? Or you could actually choose the value of the matrix. So you see here the value is 1, 0, 0, 1. The kind of transformation that this matrix does is what is represented here. As soon as I click animation, it doesn't do any transformation because there is no transformation that this type of matrix does. But let me change 1 to 2. You see that the transformation that this matrix does. See the grid lines which are there parallel to y-axis, they expand, right? So this is the transformation. Now, because of that transformation, the determinant changes. This is what, see the this value 2.5, right? When I do that transformation, look into the determinant value which is changing. The area is scaling. Now I could change any value in the matrix. All these transformations would happen. Right. And if you would want to actually play that out, you can play it like this. And then you could see the entire animation happening. How does the entire matrix changes or dislocates the entire. Now you might want to see how that transformation shifts the vector. This was the entire vector. Now let me use a smaller or something which gets moved in within the space itself. So you see that this is the original vector v. After getting multiplied to the matrix, it becomes m into v. Now this is the new position. See how does the entire transformation happens. This see how the entire transformation moves the vector from one location to another location, right? It is all based on the values that are there in the matrix. Now, if the values are like this, the transformation of the vector A would go here. But see the area between the grid lines, the highlighted region. This is the area that is enclosed in red region. That is what is called as the determinant, or the region, the change in that area. This is called as a determinant. Right now it is all changed, right? So this is the changed area. This is called as determinant. Good till here? Yes, no? I'll come back to your questions. I'll go there. Don't worry about it. Now, given that you might have heard about things like you might have heard about things like inverses, right? What do you think inverse is? Inverse of a matrix. Let's say a matrix you already have known by now. A matrix A does some sort of transformation. Formation. I'll come back to your question in a moment. A brings some transformation. What do you think inverse of that matrix would do? Any idea? Change in area. Yes, that's right. Reciprocal. That's right. Exactly. It is exactly like when A brings a transformation, A inverse undoes that transformation. Just to help you understand, there are some animations that I created, but let me show it to you here itself on this page. So let's say that, or let me show it to you for this entire lecture I created this HTML. This is what you have on your Teams channel. Inverse is, go here, go down. This is the determinant thing. Go through this document will be very helpful for all of you. But anyways, I'm going to inverses part. What basically the inverse of the matrix does. Yes, here this part. Okay. So look closely here. What happens to when you apply inverse? Apply A. A does some sort of transformation. Okay. So this is the transformation which A does. Now A inverse is just undoing the transformation. Okay, let me show it to you on the animation that I created. It might become slightly easier for you to go through and understand. Look into this undo effect. This is the animation that I created for the last batch, and it might seem slightly easier for all of you to go through the animation. The very first thing is, let's say that this is the vector that you have in green. Okay, what matrices do? This is a matrix 1.7.31. This matrix would do some sort of distortion. This is the kind of distortion that the matrix does. See where has the vector moved to, and see the determinant as well. Now inverse is just redoing and undoing what the matrix has done. So coming back to the original, reverting it all back, coming back to original position. So red is where you move to because of the transformation. Green is because the original position where you have moved back, right? So inverse is nothing but undoing the transformation. And this has much more important aspects, or much more important thing that you'll think about, because when I write it like ax is equals to b, what you can also say is x is equals to a inverse b. Now this you might have heard about, when you have to find the value of x, you can multiply x is equals to finding a inverse and then multiplying it with b. Why do you find a inverse at the first place? Because x was the original position, b is the new position. So if you can invert the transformation and multiply it to where you have reached to, you actually can get back to x. That's what you just saw, right? Now it becomes easier for you to relate, isn't it? Okay. These are the kind of things that you will be going through in the next set of classes. A lot of things that you see that I wanted all of you to understand is on these aspects. Everything that you see in linear algebra, or all the things that we'll be demystifying, whether it is studying about decomposition or studying about, again one other aspect. This will be easier for you to grasp. I told you that a gets multiplied to x, it shifts to a new position b. Okay. Now, this is an idea that might help you, because this has helped me immensely. A can be seen as a force, right? A applies a force on X, X reaches to B. Now, when you see physics, in physics, force has directions, right? Force has directions. So every force would have direction and magnitude. So A would have its own direction. What kind of force? There could, I think there is someone who is raising their. Let me unmute you. You could also type your question. I can answer that. Go ahead. Who was raising their hand?
So last point I didn't get.
Which one?
This one, AX is equals to B. That's all.
Someone was raising their hands repeatedly. I saw someone raising. But anyways, let's say what I was saying is, let's say there is 1, 2, 3, 4. When you multiply it with the vector, let's say 2, 2, you will get a new vector, right? When you multiply it, 1 into 2 is 2, 2 into 2 is 4. You will add them all together. So 2 plus 4 is 6. And when you multiply 3 into 2, 6, 6 plus 8, 14, right? So you get 6 and 14. So your your first vector gets shipped to a new position. So 2, 2 has moved to 6, 14. This is what I meant when you basically are moving. Think of it as you have a vector A here. It is getting moved back to a new position. This was 2, 2. Now it is moving back to 6, 14. Now, because it is moving back to 614, basically the matrix A, this is a matrix A which is getting multiplied to a vector X. It is shipping it to a new position B. The matrix A could be applying thing. You can also think of A as something that is applying some force on X, right? This is what is causing the distortion in the entire space. Because there is a force applied and forces have direction and magnitude. The direction of the force, in this particular case, the direction that the force being applied is called as eigenvalue. Or sorry, the magnitude of the force is called as eigenvalue. The direction of the force or the principal axes of the force are called as eigenvectors. I'll just give you a simple example. For example, let's say I have this entire two-dimensional sheet of paper and there is a vector which is lying here. If I apply a force on, stretch it on this side, what is the principal axis of force? This, right? This is the direction. Now, what would happen? This get elongated like this. The entire space gets elongated like this. The vector gets stretched like this. Now, because the vector has got stretched, it has got moved to a new position. Now, the force was being applied in these two directions itself, right? The direction of the force is the direction of eigenvector. So the eigenvector would always be the principal axis of the force. The eigenvector would be this. And what is the value of the force applied? That is eigenvalue. So all the things that you have learned, eigenvectors, eigenvalues, decomposition, all of these things would start making sense when you easily understand the concept of Ax is equals to B. So basically A transforming the space such that X moves to a new point B. Now there could be special type of transformation. Think about it. When you rotate the entire input space, right? Let's say there's a vector here. You rotate it 45 degrees. This has moved here. Now, what do you think would be, what is the direction of a force applied? When you rotate, where would be the direction of the force applied? It's a toggle, right? It is along the z-axis. It's a toggle because the direction of force applied cannot be seen on this piece of paper. It is towards the z-axis. If you put the thumb around and you rotate, the principal axis is around the z-axis, right? Hence, there are no eigenvectors. There are no eigenvectors. All the things that you have learned about eigenvectors, there are no eigenvectors while you are rotating. Anyways, these are the things that you will be learning. But at least from the basic point of view, you understood what exactly is linear algebra. Linear algebra is linear transformation. I generally give this in as a part of the first lecture. What means linear transformation? Linear transformation is when you have input space which has grid lines which are parallel and equidistant from each other. After doing the transformation, these, let's say this is how it has stretched, they become parallel and equidistant after the transformation itself. Okay, this is linear algebra. When your input space gets changed like this, let's say that this is your input space. Now, because your input space has changed and the lines are not parallel and not equidistant, this is non-linear transformation. Okay. Now, linear transformation gives rise to linear equations, which is what you study in majority of the applications like linear regression or other types of things that you will be doing in your machine learning. But nonlinear transformations are not studied a lot profoundly. Okay, so this is what we are not learning about, but we are learning about linear algebra. This is what you will be going through. Understand what is the basic of determinants. Determinant is how does the area changes, how much the area enclosed within these grids the changes, how does it scales to. Let's say this area is 1, right now it has changed to 4, so it has changed by 4 units, hence the determinant is 4. Okay, what is inverse? Inverse is undoing the transformation. So if you want to move back to original state, you will apply inverse, right? What is rank of a matrix? You have already studied about it. What is rank? You have studied in lecture 0. Some of you have studied in lecture 0. What exactly is rank?
Number of non-zero rows.
Number of non-zero rows.
That is a bookish definition. What exactly? What do you understand by rank?
I have no
It's
idea
like
what is rank.
it's
Why
like
while yeah, while the transformation is happening, think of it as while the transformation is happening, let's say that this is a 2D space. The transformation has resulted in a 2D space. So initial space was 2D, the output space is 2D, hence rank is 2. But there are cases when this entire, let's say if I stretch this thing up such that this becomes a single piece of line. I stretch it in bone from both the sides such that it is stretched up such that it becomes a very long, thin piece of line, one dimensionally. Okay, in that case, you started from 2 dimension, resulted into 1 dimension. Because the output is 1 dimension, rank is 1 dimension. Rank is how many dimensions you are left with when you apply transformation. Okay, for example, what do I mean by that is, see here, quickly see here. See, if I use a matrix, okay, you said the number of non-zero rows or columns, right? So let's say that I have this matrix, I am applying the force, okay, and this has collapsed the entire space. My 2 dimensional space has now gone moved into 1 dimensional space. This is what has happened if you see here, right? My 2 dimensional space has gone into 1 dimension. So the output space is 1 dimensional space. Okay, so the rank is how many dimensions the output space has. If I change the matrix by something, the output space is still 2 dimensions. It's a still stretched or slightly different looking shape, but the output space is still 2 dimension. As soon as I move it such that the output space becomes 1 dimensional, it becomes this. The output space could also become, let's say, if I stretch it too much, this can become a point itself, right? There are no dimension attached to it. When the output base space becomes 0 dimensional, hence the rank becomes 0. So there are cases when the transformation can, let's say you start from 3 dimensions, you can actually uh, transform that space into a 2 dimensional word. You can transform that space into a 1 dimensional word, or you can transform that space into a 0 dimensional word. So your rank would be after the transformation, how many dimensions that you preserve. That is what is called as rank. And how does it relates to what you have studied in the book? The number of non-zero rows. What happens is number of actually the number of non-dependent rows or columns. Let's say that you have the matrix which has 2 1 4 2. If I apply this matrix onto the same page, see, and this is that page, right? So let's say that I have a matrix, I do not have the flexibility to go to 4. Let's say that I have 2 here, okay, and let's say that I use 2 1, and here itself 2 1. Okay, this is the matrix that we have, and let's visualize this 2, and then this is 1, then the other element is also 2, and then this is 1. You're able to see this, right? Oh, sorry, I'm slightly overdone that, but the output is 1 dimensional. Now what happens here? See, both the rows that you see are basically describing the same vector in the matrix. They are pointing to the same vector. If you would plot this out, let's say this is 1 2, This is 1, 2. This is your 2, 1 vector. The second, this is first row, right? This is the first vector. The same vector is there. Even if I have thing like 2, 1 and 4, 2, the first vector is this, second vector would be third and fourth, and 4 and 2 would be here. If you think about it, it would be here. So it's a stretched or a scaled version of the same vector, right? If you think about the first row is a half of second row is a twice of first row, right? So rank is nothing but how many linearly independent rows or columns that you have. Right now, they are not independent, because if you think about row number one, row one is equals to 2 twice of row number 2, right? Because they are somewhat dependent. They are somewhat dependent by, if you can scale the first one, you would be able to reach to the second one. Okay. What do we mean by scaling a vector? Let's say there is a vector called as 2, 4. When you multiply with the scalar number, let's say 3, what happens? It gets multiplied to both the dimensions, and you get 6 and 12, right? So this is what is scaling. So basically what I'm saying is, if you scale the first vector, you basically are able to reach to the second vector. So there is a dependency between them. When there is a dependency, your matrix would always collapse the entire region. Okay, and this is how it would look like. And hence, in that case, the rank would be, what would be the rank? Rank would be 1, right? Good.
One.
This is all good. Yes, no.
Yes, sir.
One because we have stretched it to one dimensional array. I mean, like I don't get that why it became one.
See, this is because this has become one-dimensional array or one line itself, right? That's right. So it has become one line. So basically, if you think about the information which is, there is no new information in the matrix, and this is how it is related to machine learning as well. I'll just take 2 more minutes and then we'll finish up the lecture, so that I have another lecture starting up in next 8 minutes of time. So let's say that you have a house which has 1800 square feet, again linking back to this thing that we started, 2 rooms. Another house which 3600 square feet, 4 rooms. If you think about both of them, both of the rows are nothing but, one is a smaller piece of house. Okay. The second one is a scaled version of it, exactly twice of the first house. Okay. Now this is house number A, this is house number B. Both of these houses are dictating the same thing. It's just that the first house is this. If you think about the price of the houses, this could be of 2 crores. If this is of 2 crores, the second house would be of 4 crores. That is how linearly proportional things would be, right? So you can easily guess that if 1800 square feet of house with 2 rooms is of 2 crores, then 3600 square feet of flat with 4 rooms, it would be of 4 crores. That's what it's going to be, right? This is how linear things happen. Now you have got 2 and 4. You are not getting any new information from here. If are you getting any new information from these 2 rows? No, right? In machine learning, the similar sort of thing happens. What we get to is, are there any new information which are represented in rows? And hence, we only look for new information for the models to learn from. These are the things that we don't want the models to run from. So how rank is useful is, it will help you understand what are the new information. There is only one new information in this entire matrix. Rank will tell you, if you have 100 dimensions, 100 rows, how many rows are unique, how many are actual information from where I can learn, or my models can learn from. Is that intuition good? Yes, no?
Yes.
Yes.
Yeah.
So it is like rationalizing the matrix to get a unique information, right?
Exactly, that's right. That's absolutely right. So sorry about it. I have to move to the next class. We'll get into. I have to take the breakfast as well, but I'll get into these discussions in the next class as well. So keep studying about it. What you can do is go to your team's channel, again saying that this is what your all the things that I was trying to explain, you would get everything, all the help from this particular folder called as lecture 1. There is the slide here, which is what we'll be covering in the next class. I do not cover the first lecture straightly because I don't think that people come prepared for getting introduced to linear algebra that the way it should be taught like. And then this is the component document, basically a summarized version of your lecture. And this is the HTML. This is what you will be using to interact and learn from visuals. Okay. This is
Can you
how
add
the
a
entire
whiteboard
context
and
is going to be. Yes, yes, I'll be sharing the whiteboard and I'll be including it here itself. Okay.
Thank you, sir.
Sir,
Thank you,
but
everyone.
you
Thanks
be
for joining.
sharing the us the access to the
Thank you,
MS
sir.
Teams as well, because I don't see I have the access to it.
If you don't have, I'll definitely give you the access. Don't worry about it.
Yeah, thank you,
Can we
sir.
also have this Miro file, please? The folder
Yes, yes,
is
that's
very
what
helpful.
I'm sharing. Yes,
Thank you.
yes. Okay.
Miro file which you brought now. Yeah.
Thank you,
Yeah,
sir.
yeah.
Thank you.
Thank you, everyone.
Thank you, sir.
Thanks a lot,
Thank
sir.
you.
It
Thank
was
you.
really wonderful.
Thank you, sir.
Yes, sir.
Thank you so much,
Thank
sir.
you, sir.
Thank
Thank
you.
you, sir.
Thank you.